In the last session, we have seen that obtained by the auto transformer. What is the difference between the auto transformer and two winding transformer? Also, we've seen that how the copper is saving in the auto transformer for a transferring the same amount of power using the auto transformer. Once again, we can recap those things, and that is comparison of the two winding transformer with the auto transformer. We are taking the same kVA rating with the input voltage of V1 and the output voltage of required voltage is V2. The rated current to be supplied to the load is I2 and the current which is drawn to supply I2 load is I1. Then we know that kVA to be handled by the both types of the transformer by primary and secondary is the V1 I1 must be equal to V2 I2. It is rightly pointed out that the kVA rating of the primary as well as the secondary is remains same. That is, the rating of the transformer is in terms of the kVA. The kVA is nothing but it's the product of the primary voltage and the primary current. That should be equal to the secondary voltage multiplied by secondary current. And if we are comparing the two transformers, that is, one is the two winding transformer, the another one is the auto transformer. That is, what is the MMF balance equation for two winding transformer and auto transformer? In the case of the two winding transformer, if you are looking into the two winding transformer, the ampere turns of the primary is nothing but it is a product of the number of turns of the primary multiplied by the current. Therefore, it is N1 and I1, and the ampere turns of the secondary is the number of turns in the secondary multiplied by the current in the secondary winding. Therefore, there is a balance between the N1 I1 and N2 I2. Therefore, for two winding transformer, what I am representing here is N1 I1 is equal to N2 I2. Then if you look into the auto transformer, once again the MMF balance equation is for the winding BE and EC, because they have got only one winding here. Therefore, you have to make the balancing equation of the MMF between the winding BE and EC, that is B to E and E to C. Then MMF of BE, if you are taking the number of turns in the BE is, it is N1 minus N2. It is N1 minus N2, because the total number of turns between B and C is N1 and the number of turns between E and C is N2. Therefore, what you have to take, it is N1 minus the N2 here. Sorry, N1 minus N2 is the number of turns between BE. Therefore, MMF balance equation is N1 N2 into I1. That is, we know that number of turns here it is N2 minus N1, sorry, it is N1 minus N2. The current which is flowing in this BE is the I1. The ampere turns is nothing but N1 minus N2 multiplied by, that is I1. This is I1. The same thing what I am writing here, that is here. Okay, this is how we have to write the MMF equation for the auto transformer. Okay. Therefore, the MMF of this one is N1 minus N2 into I1, whereas the MMF of the lower portion, that is EC, which is a common factor for both primary and secondary, the number of turns here is N2, the current is I2 minus I1. Therefore, here MMF balance equation is the N1 minus N2 into I1 multiplied by, it is N2 into I2 minus I1. Then if you are simplifying this equation, once again we are getting the balance equation as N1 I1 is equal to N2 I2. Then this identity of equating the MMF of the primary and secondary, this identity I am using in the next slide. Now I want to find out the what is the amount of copper required for the two winding transformer as well as the auto transformer. I am comparing the two transformer in terms of the copper requirement. Here, the volume of the copper is required as it is proportional to the cross sectional area multiplied by the length of the conductor. Therefore, the length of the conductor is depending upon the number of turns, and the cross sectional area is depending upon the current carrying capacity. The same thing is written here. The length of the copper wire is proportional to the number of turns, and the area of the wire is proportional to the current. Therefore, the volume of the copper required is proportional to the length of the wire multiplied by cross-sectional area of the conductor. Therefore, the volume of the copper is proportional, length is proportional to the number of turns, and the cross-sectional area is depending upon the current carrying capacity. Therefore, the volume of the copper is proportional to N into the I. Then this identity that we have to make use for both two winding transformer and the auto transformer. That is what I am writing here is amount of copper required in an auto transformer. That is what is the copper required here in the auto transformer. It is proportional to the number of turns multiplied by the current in this winding and number of turns multiplied by the current in this winding. Therefore, for this portion of that is between B and E, the number of turns is N1 minus N2 and the current is I1. Therefore, copper required for this portion is N1 minus N2 into I1, and the copper required for the lower portion of the auto transformer, that is EC, is nothing but it is N2 into I2 minus I1. The same thing I am writing here, that is it is N1 minus N2 into I1 plus N2 into I2 minus I1. This is for the copper required for the auto transformer, that is a numerator. At the same time, amount of copper required in the two winding transformer, it is nothing but it is number of turns multiplied by current in the primary plus number of turns multiplied by current in the secondary. The same thing is written here, that is N1 I1 is the copper required for primary, N2 I2 is the copper required for the secondary, the two winding transformer. Then I am using the identity as N1 I1 is equal to N2 I2. Therefore, the N2 I2 I am replacing by N1 I1. Then if you are adding this, what I am getting is 2 times N1 I1. Then in the numerator we have got 2 and I1 is a common I am taking outside, and 2 I1 in the denominator get cancelled. Then what is left out is N1 minus N2. Then I am dividing both numerator and denominator by N1. Then what I am getting here is 1. I am getting N2 by N1. N2 by N1 is nothing but K. Therefore, it is 1 minus K I am getting here. N1 divided by N1 is 1. Therefore, what I am getting is the amount of copper required in the auto transformer to the amount of copper required in two winding transformer is equal to 1 by K. Therefore, I am interested in what is the amount of copper required in the two winding transformer. Then in terms of the copper required in the two winding transformer, that is 1 minus K times amount of copper required in the two winding transformer. Therefore, weight of copper in the auto transformer, that is I am representing by WA, it is 1 minus K times weight in ordinary transformer, that is W0. Then WA is equal to, that is this is WA, that is 1 minus K is as it is, then it is W0, that is I am writing in the equation as WA is equal to 1 minus K times W0. Then the saving of the copper is nothing but it is a W0 minus WA, that is the copper required for the two winding transformer minus the copper required for the auto transformer. What I am getting is W0 minus 1 minus K into W0. Then if we are simplifying, then we are getting K times W0 is the copper is saving if you are using the auto transformer for transferring the same amount of the power. That is the copper saving is K times W0. This is how we have to derive the equation for copper saving. Then we will move to the saving of the copper is, it is K times weight of the copper required in the ordinary transformer. Then we move to the output of the auto transformer. The output of the transformer is nothing but here it is V2 into I2. The output of the transformer is V2 and I2. Then it is in the case of the auto transformer, the V2 I2, that is a power, that is apparent power what we are getting across the secondary. It is not only the transferred by electromagnetically, but it is also transferred the electrically. Therefore, the transfer of the electricity from primary to secondary in the auto transformer is not only from electromagnetic, it is by the electrical also. Then how much power is transferred by electrically? How much power which is transferred by the electromechanical induction? Electromagnetic induction. That is, electromagnetic induction power which is transferred is given by, it is a voltage across the common winding, that is V2, and the current which is flowing through that common winding which is between the primary and secondary. That is nothing but V2 into I2 minus I1, which is the power which is transferred electromagnetically. That is electromagnetic induction. Because of the induction, this power is transferred, that is V2 into I2 minus I1. Then the remaining power is transferred by the directly electrically. That is what we are calling this the conductivity. That we are seeing now. Okay. That is the output apparent power of the auto transformer is V2 I2, and the apparent power transferred inductively, that is I told you it is a voltage across the secondary winding, that is a common winding, multiplied by the current in the common winding, that is I2 minus I1. Therefore, here the V2, then I2 as it is, I1 can be represented by K times I2. I1 can be represented by K times I2, because we know that I1 by I2 is equal to K, therefore I1 is equal to K times I2. Then here the I2 is common, therefore I2 is taken common, therefore V2 I2 1 minus K. That is apparent power transferred inductively is equal to V2 I2 into bracket 1 minus K. Then V2 I2 is equal to V1 I2. That also we have derived that identity. Therefore, it is V2 I2 can be replaced by V1 I1, that is equal to V1 I1 1 minus K. The V1 I1 is nothing but an input to the transformer. It is V1 I1 is nothing but the input to the transformer. Therefore, what I am writing is the power which is transferred inductively or inductively, that is given by input times 1 minus K, or 1 minus K times input, or it is 1 minus K times the input. This much power is transferred inductively. Then how much power which is transferred the electrically, that is V2 I2 minus this input times 1 minus K, that much power which is transferred the electrically, that will be the power transferred conductively, that is electrically, is equal to input minus 1 minus K times input, that is which is transferred already inductively. The remaining power is transferred by the electrically. Then if you are putting, that is input is a common in this both the terms, input I am taking outside, what is left out is 1 minus of 1 minus K. Then if you are simplifying, then what we are getting is the power which is transferred conductively or electrically, it is K times input. The magnetically it is transferred 1 minus K times, and electrically it is transferred K times input. If you are adding this 2, then you are getting the total power transfer, that is V2 I2. Means the 1 minus K times the input, which is the power which is transferred magnetically, and K times input which is transferred the conductively. Then if you are looking to the equivalent circuit of the auto transformer, it is similar to that of our two winding transformer. First you have to calculate what is the equivalent circuit of the two transformer. For that we have to find out current ratio and the voltage ratio. The current ratio is nothing but it is a current in the BE to current in the EC. That is current in the BE divided by current in the IC. That is, it is the primary current to the secondary current. That is nothing but here secondary current which is a common to the both primary and secondary. The current which is flowing between B and E is I1. The current which is flowing between E and C is I2 minus I1. Therefore, I am taking I2 minus I1. Just I am dividing both numerator and denominator by I2, so that here it is I1 by I2 is equal to K. It is I2 I2 get cancelled. Therefore, you are getting 1 here. Once again, it is a transformation ratio K. Therefore, the transformation ratio for the current what I am getting is K minus 1 minus K. Similarly, if you are taking the voltage ratio, it is secondary voltage to the primary voltage. That is nothing but it is a voltage between EC to B. EC to B. That is EC to B. That is it is proportional to the number of turns. Therefore, the voltage in the CE is proportional to N2. Therefore, it is N2. The voltage in the B is proportional to N1 minus N2. Therefore, I am writing here N1 minus N2. Once again, I am dividing here N1 to both numerator and denominator, so that what I am getting here is N2 by N1 is K, N1 by N1 is 1, and N2 by N1 is 1 minus K. Means the voltage ratio and the current ratio in the auto transformer, what I am getting is K divided by 1 minus K. With the help of the same as your R1 X1 is the primary resistance and reactance of the auto transformer, the secondary resistance and reactance can be replaced by its equivalent resistance referred to the primary side by dividing the square of the transformer resistance ratio. What is the transformer resistance ratio here? It is K minus K divided by 1 minus K whole square. It is in the case of auto transformer that we have derived here. That is K divided by 1 minus K is the transformer resistance ratio. That you have to divide here. Therefore, it is K divided by 1 minus K, it is whole square. That is, it is an equivalent resistance referred to the primary side of the auto transformer. Similarly, the reactance also you are transferred to the primary side. With the help of this vector diagram, just I want to draw the vector diagram for this. That is, you have to flux, you have to take it as a reference, then you have to take what I want is the induced voltage, that is a voltage across EC because of V2. That is, you have to start with a V2. We know the V2, I know the value of the I2, and the power factor angle between V2 and I2 is also known. Because I know the load condition, from that I am building up the vector diagram. Therefore, it is a V2 and it is I2 and the phi 2 I am trying. Then to this V2, I am adding the drop of the resistance drop of EC, reactance drop of EC. Resistance drop of EC and reactance drop of EC, that is nothing but I2 minus I1 into the resistance of EC, I2 minus I1 into the reactance of EC. To add to this V2, what I am getting here is, that is ECE, that is a voltage here. Then the voltage between B is in the same phase with ECE, therefore I am representing here EB. Then I have got the counterbalancing current. Then I have got EB, I am EEB, I am producing the negative side. Then this EB, I am adding the drop of resistance drop of BE, reactance drop of BE. Then what I am getting is the voltage between B and E, that is a terminal voltage VBE, that is voltage EVEB. To this, if you are adding the V2, then what I am getting is the V minus V2, that is I am producing this and to the tip of EB, so that what I am getting here is the value of V1. That is what I am getting is the value of V1. This is how we have to draw the vector diagram for the auto transformer. It is simple. Start with this voltage across this, and terminal voltage between B and E. To B and E, if you are adding V2, then what I am getting is the V1. This is how you have to draw the vector diagram for the auto transformer and draw the equivalent circuit diagram of the auto transformer.